Okay, I think we're in business. So this is try number 6 at recording this video. The first 3 tries were all on Screencast-O-Matic, and my computer is having issues with its RAM, and thus it blue screened out 3 times. The 4th time, I came up here, tried to record it with the front-facing camera on my phone using this nice little whiteboard right here, and realized that all of the characters were backwards. 5th time I wasn't recording. So this is number 6. We're going to do it this time. It's going to be a great video, and I hope you enjoy it. So this is the first supplementary video for Physics Tier 2. What I want to talk about today is, well, I realized that you guys were talking a lot about resistive forces, right? You were talking about friction. You were talking about buoyancy. And AP Physics 1 and even normal physics sort of leaves out this nice concept of air drag, which is one of the most common forms of resistive force. So I think it's natural for you guys to be curious, what is air drag and why aren't we learning it? And frankly, you're not learning it because mathematically it's really, really complicated. Even some of you who are in calculus, you might recognize some of the concepts that I'm going to talk about here, but you're probably not going to be able to solve them. And by probably not, I mean you definitely won't be able to. It's why we have computers. None of us can. But air drag is an interesting concept that I think is really fun to touch on. And since you guys aren't learning about it officially in class, I thought that I would do a little supplemental video and sort of get you guys into the concept of air drag. So, air drag is a very, very intuitive concept, thankfully. All of the things that it's based on are very intuitive. They make a lot of sense. Which is really, really nice. The issue is, of course, the math that arises. And when I thought all was set, all was good, my girlfriend called me during the last video. So we're gonna just pick up where we left off because I'm sick of starting this over. So as I was talking about before, air drag is thankfully a very, very intuitive concept because all of us have experienced it at one point or another. It's kind of just realizing which things actually make the drag force change, which is pretty simple to understand when you think about it. So what I was about to draw is this little diagram right here. I have just some object moving through space, and we're going to say this is moving at some velocity. This is going to be a pretty big velocity. Now, it's not just moving through space, it's moving through some kind of medium that is not a vacuum. A vacuum, there would be no drag because there's nothing to drag it. But when we get in the atmosphere of Earth, or, on the surface of the Earth, there is air drag. There's quite a lot of it. So what we're going to end up getting is a force that opposes the velocity, called drag. So I usually denote that with a capital D. Okay, so how do we really, what's the word I'm looking for? How do I make numbers of D? I don't know. Well, this is equal to the negative of some coefficient times the velocity. But it's not that simple. There is a lot going on here. And there's a lot of ways that this equation is actually very dynamic. It changes based on the situation. If one landscape has significantly more air drag than another landscape, this equation, while there is something that is defined as, how much air really pulls on things, blah, 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 the equation itself might entirely change. It might not just be one variable. The entire equation might change. So I want to go ahead and denote what I even mean by this C right here, and then I want to explain this sort of proportionality going on here. So first of all, the C is equal to a bunch of things. The first thing is, well, the variable of just how much drag does this medium create. And this is sort of like the coefficient of static and kinetic friction. It's pretty arbitrary, and you just know that if the value is bigger, you're going to have more resistance. That's really all that it's talking about. So I usually denote this as C sub D. The second thing that it's equal to, or proportional to, I should say, is the density of air. So you guys haven't really touched on density yet, but most of you have probably touched on it in previous classes like chemistry or something like that. Density is just how much mass do you fit into the unit area, right? The unit area being 1 meter cubed. Or volume, I should say, not area. So rho is some amount of mass divided by some amount of volume. I believe for air, generally that sticks around 1.2 kilograms per meter cubed. So that's actually pretty large. If you take a meter cubed of just air, it weighs about 1.2 kilograms. All right. And the last thing this is proportional to is the cross-sectional area of whatever object is moving through the medium. So I'm probably going to return to this analogy a couple of times because it's really, really helpful to understand what's really going on here. If your hand is stuck out a window while you're in a moving car, right? You feel a drag. You really do. Because the air, while it's not really moving itself, there might be no wind at all, the air is in relative motion with you. So you're going to feel it almost as like this wind against your hand. Even though the air itself is not moving, you're moving. And when you have your hand out, it hits it and it pushes it back. But what if you take your hand and you just do this? Well, now, a lot of that wind that was hitting all over your hand before is missing, and only this tiny, tiny plane is left. So with a smaller cross-sectional area, whatever object is moving through the medium, you're going to have less drag. So these are the three things that this is really based upon. So you can expand this equation if you really want to. This drag is equal to the negative coefficient of drag times rho, which is the density, times the area, the cross-sectional area, I should say, times the velocity. So what does this really mean? Well, this says for larger velocities, things undergo more drag. And this is actually a concept you guys have probably thought about before, which is terminal velocity. How fast can you move before the force of gravity, what's pulling you down, is equal to the drag force, in which case you stop accelerating and you just keep going at a constant speed. What speed is that? Well, you can find it by solving this equation for v. Also, this negative right here, you guys have already talked about Hooke's law a little bit, so you guys know what that negative probably means. The negative just implies this is a resistive force. This is in the opposite direction of whatever variable is changing, and in this case, that would be the velocity. This is in the opposite direction. A lot of times you're not going to see this equation actually with that negative. You're probably going to see it completely without. But I think it does make intuitive sense to keep it in there. A lot of times also you're going to see the v written with these little bars around it. This does not necessarily imply absolute value. It actually implies this is the vector. So this right here is short for the square root of vx squared plus vy squared. You guys have probably seen that before. This is anything moving through area that you can break down into an x and y component. It's just shorthand for that. So a lot of times you're going to see it written like that too. This is the vector v. All right. So what do I mean by this equation can change based on the situation? Well, a golf ball undergoing some kind of air drag, a golf ball is actually undergoing a ton of air drag based on just the geometry of it with its weird grooves and stuff. It goes through air really, really weirdly. And thus it follows an equation that we can't really decipher ourselves. We know that these three things are proportional to it, and we know that the velocity has some kind of relationship to it, but do we know what that is? No. So usually the approximate equation we use, I'm going to use a red marker for this, or at least the approximate equation that I use is d sub g, where g is a golf ball, is equal to 1/2 this coefficient times the density of air, the cross-sectional area, v squared, not just v. So this shows for smaller changes in velocity, we have more and more change in drag, right? If we double this velocity, we get 4 times the drag, which is not true for like this equation right here or this equation right here. If you double the velocity in this equation, you get double the drag. That's it. Which is definitely a strange concept. It's kind of weird to wrap your head around. But based on the situation, you can have different powers of this velocity. That's why I didn't specify that this was a linear relationship earlier, because depending on the situation, it's not. So this equation I used a lot last week during my physics lab. So I'm going to give you kind of like an insight into this. Every week I have a physics lab, and you know, being not in person, it's a whole different story, but regardless of whether I was in person or not, we use this program MATLAB a lot. So MATLAB is a computer language, a programming language that is used especially for things like vectors, things like matrices, and it's really, really good for any kind of linear algebra, which is phenomenal for physics, because physics has to do a lot with vectors, which is linear algebra at its core, as well as vector calculus, which is built off of linear algebra. So we used this equation, even though the example text essentially used this equation. And we had to find and plot using differential equations, which is a very abstract form of math, to create plots of the position or its energy, or what is the best angle to throw this at. You get some interesting results. So I want to go ahead and erase this. I am going to paste this equation back at the top though, because I want to talk about this specific scenario here. So I had the drag of the golf ball is equal to 1/2 this coefficient of drag, rho, cross-sectional area, v squared. That's terrible handwriting, ignore that. So what we had to build this off of is, well, what's the acceleration at any point? When we talk about projectile motion, right, we usually just talk about g, because that's the only acceleration it's undergoing. 9.81 meters per second squared directed directly downwards. That's not what's actually happening on Earth, right? Because there's air drag. So what we set up is that if we have some object moving, the force of gravity is downwards, the drag force is upwards. Usually the drag force is less than the force of gravity, otherwise it would be moving at the terminal velocity. If the drag force was more than the force of gravity, it would be moving upwards, which is really strange, or at least it would be accelerating upwards. It's kind of weird. So yeah, drag is usually less than the force of gravity. Well, I know by Newton's second law that the net force between these two is ma, and this has to be equal to, let's consider down to be the negative direction. So it's mg minus the drag force. So in the example that he used just a linear relationship. So this was b times v, where b is just a coefficient of some kind. But for what we had to do, we had to mention that squared relationship, which changes things entirely. So that's what I'm going to keep up with here. And you can solve by dividing everything by m. A equals g minus b over m v squared. This is our acceleration now. And some of you might know, some of you probably don't, but some of you might know, this is what's called a differential equation. A differential equation is any equation that has to do with something changing in the equation. So f equals ma is a differential equation, because a is based on how quickly the velocity is changing, which in turn is based on how quickly the position is changing. So since it goes through those sort of two steps, we call this a second order differential equation. You guys are not going to think of it like that, because usually your acceleration is constant and you're not basing it on anything else. But for any of you who are in calculus, you might even recognize this is a differential equation. So what you end up getting after you go through this lab, the first thing you're asked to do is plot just the position over time. And you'd probably expect a parabola, right? No, that's not at all what happened, because there's this air drag happening in both the x and the y directions. So what you get is this thing that starts to look like a parabola, and then it just kind of drops off. Doesn't look right at all, but it sort of just drops off, right? And admittedly, it doesn't look like a parabola. It really, really doesn't. And you might even compare the two. If this is what it looks like without any air drag, this is what it looks like with air drag. It doesn't go as far, it doesn't go as high, nothing. Which is, it's pretty weird. It's pretty weird to think about. So the reason that we can't plot this ourselves is because this is an extremely complex differential equation. And differential equations are very, very difficult to solve by hand. So we went ahead and we used our computers to figure this out, which is pretty interesting because you notice a lot of things. You're going to talk about conservation of energy a little bit later down the line, and you're going to realize, oh yeah, energy is not conserved through air drag because the ball heats up the air, which is a super funky concept for you now, but by the end of the semester, or whenever you guys end up learning about energy, it's going to make a lot of sense. All right, I think that's my spiel for you guys. So I did mention terminal velocity a little bit. I don't want to go too much more into detail with that. That was the only thing that, like, you might touch on later on in this class. So I'm not going to go super into it, but I just want you guys to see where some of this really, really complex math that you might end up learning in college can be directly applied to physics, as well as giving you kind of like a taste of where I'm coming from, what I'm doing in math. So I hope this intrigued you or scared you or something. Maybe you had an emotional reaction to it. Regardless, I will do more of these. I just need to figure out how my computer is going to work because I don't like doing this analog like this. All right, I think that's all I've got for you. All right, so last little video here. I just wanted to show you guys this MATLAB document. I would have shown you this much easier had I been able to record on my computer, but here we are. So this is my differential equations document. This is what I used for my lab last week. So this is entirely original. I did this all myself, just tooting my own horn. So our first thing that we had to do is plot the position. So there's a bunch of code, a bunch of defining variables, all this crap. Look at that. So that's actually what happens under a squared velocity relationship with a drag force. It goes up like it is a parabola, and then it drops off. Interesting. So then there's energy, which isn't a thing that's really going to concern you now. Then we were asked to just do it with 10 different angles, and you notice literally all of them, aren't parabolas. None of them are, which is super, super cool. And the last thing we were asked to do is find a function for the range, and from that, we could find out what the best angle to throw something at would be. So you might already know that the best angle to throw something at in real life, or not in real life, but in a non-air drag ridden medium would be 45 degrees. That gets the farthest. In this case, it's about pi over 6. Know that 45 degrees in radians is pi over 4. Pi over 6 is quite a bit less than that. So throwing it under 45 degrees is actually the best way to get this far with this squared relationship. All right, that's all I've got for you.